So we're going to finish our gas laws notes where we left off from last class. We left off on the ideal gas law, and if you recall, the ideal gas law involves all the variables that we've come across from all the other gas laws: pressure, volume, moles, ideal gas constant, and temperature. None of the variables are held constant in the ideal gas law, except for really the ideal constant, gas constant here, R. So to do gas stoichiometry, if you recall what stoichiometry is, it's where you take a balance equation. So you take a balance equation and then you go ahead and ratio it mole-wise. So the part of the ideal gas law that's essential is N. So if we can solve for N, we can do stoichiometry from there. Now, how do I know a problem like this involves stoichiometry? I see that I'm asked to find the mass of sulfuric acid, given information about hydrochloric acid. So because of that, you see two different substances requiring a balanced equation. So we're going to have to write a balanced equation to start. So it says that what mass of sulfuric acid is needed to react. So we know that H2SO4 is a reactant. And it's going to react with NaCl, as stated right there, to produce HCl and some other product. And so if you look at this reaction, it's a double replacement reaction. And so when we replace these two parts, the cations, you will see that sodium is now with sulfate ion, and sodium has a +1 charge, sulfate has a -2 charge, so it's sodium sulfate formula like this. It's a neutral compound when it's doubled the sodium. So we're going to have to balance this equation out. In balancing this equation, we'll notice that we're going to have to double the sodium chloride and the hydrochloric acid, and everything else is 1. So we're given a lot of information about hydrochloric acid, but we're asked to find the mass of sulfuric acid. So the first thing we want to do is take the information that we know of hydrochloric acid, and then we're going to find the moles of it. So here's my volume, here's my pressure, and here's my temperature. So with all that information, I can use the ideal gas law to figure out the moles. So from there, I'm going to take you can rearrange this equation if you'd like, but really you're just taking 1.51 atm, which is the pressure. Here's my P. My V has to be in liters, so it's 0.340. And I know my V is in liters is because my R constant tells me exactly what my other units have to be in. N is what I'm trying to solve for, and I'm going to label N as hydrochloric acid. And then my R, the R constant, given that the pressure is in atm, is 0.0821 liters times atm over moles times Kelvin. So from there, I figure out that temperature has to be in Kelvin units as well. So adding 273 to 20 degrees Celsius, I get 293 Kelvin. And you'll notice how the units cancel themselves out. Liters on top, atm on top, on both sides of the equation will cancel out, leaving us with moles as the final unit. So when you solve for N moles of hydrochloric acid, you will then get this number, which is 0.0213 moles. Please make sure you go through the calculations to practice your mathematics. Now you take this hydrochloric acid and you just ratio it with sulfuric acid. And notice it's a 1-to-2 ratio, or 2-to-1 if you want to look at the other way. But you ultimately want to do the mole ratio. So I'm going to do this using dimensional analysis. So here I have 0.0213 moles of hydrochloric acid. I'm going to multiply it, again, converting the units, the mole ratio between the two. For every 2 moles of hydrochloric acid, there's 1 mole of sulfuric acid. Now with that, I don't want moles because currently I have moles of sulfuric acid. So if you cross cancel these two units, you have moles of sulfuric acid. You really want grams. So 1 mole of sulfuric acid has a molar mass. So we're going to look on the periodic table for this value, 98.09 grams of sulfuric acid. Now when you do the calculations and finish this problem up, you get 1.04 grams of sulfuric acid. So that is, the stoichiometry part is right here, right when you do the mole ratio. And then, of course, the gas part is just using the ideal gas law to calculate information, moles specifically, of the one of the substances, which is a gas. Now, so ultimately, in this little image, moles can do stoich, and in order for moles to do stoichiometry between reactants and products, we need something called the mole ratio. And that's this right here, the mole ratio using the balance equation. So we'll continue on. So that was non-STP conditions. You'll need to rely on this equation to use when you're doing non-STP conditions. Now we're going to go into STP conditions. At STP conditions, a mole of a gas has 22.4 liters. Now you're going, what does it mean? Well, STP stands for standard temperature and pressure. That means that you have 0 degrees Celsius and 1 atm of pressure. Now, the 0 degrees Celsius could be 273 Kelvin as well. Now, how did I get this relationship between a mole equaling this much volume? So this is my V, this is my N. So N is 1, T is 273, P is 1 atm. If I plug it all into the ideal gas law, you'll notice, and I'll do that right now, P, once again, is 1 atm. V is our unknown. We don't know what that is. And then N is 1 mole. R is 0.0821. And then T is 273. So we have our STP conditions. So solving for this V, you'll notice that you get 22.4 liters. So as long as we're at STP conditions, where it's 1 atm and 0 degrees Celsius, our volume for every 1 mole is always going to be 22.4 liters. Now this makes it really easy for us. And when I say really easy, because now we have a converter. This is our converter for STP conditions. So let's go ahead and take a look at this. I'm actually going to start off with the image first as a way to help us. So the first thing you want to do in a balance equation is to balance this equation. And in doing so, you get a 2 to 1 to 2 mole ratio. So this is a 2 to 1 to 2 mole ratio. Now when the conditions of temperature and pressure are constant, the volume is going to be the same proportion as the mole ratio. So if you look at this, the volume ratio is going to be the same proportionality here. So for every 2 liters, you would need 1 liter of 2 liters of hydrogen, 1 liter of oxygen to form 2 liters of water. So you can actually do volume ratio easily because pressure and temperature are constant. And precisely that, we're going to do it with this problem. So it says right here, how many liters of water vapor will be produced if 15 liters of hydrogen and 8.9 liters of oxygen reacted at STP? So one of the key is knowing that it's at STP. And now you're given both reactants. So this is a limiting reactant, and you're given liters of both of them. And we know that liters could be interpreted in the same manner as moles here because they're proportional when temperature and pressure are constant. And you can, because we're at STP, temperature and pressure are no longer changing. They're at the same set of conditions. So we can take this, and if you remember limiting reactants, you just take your 15 liters and divide it by the stoichiometric coefficient. So divided by 2 gives you 7.5. 8.9 divided by 1 is 8.9. So which one's lower, 7.5 or 8.9? And you're right if you said 7.5. So this must be my limiting reactant. Using my limiting reactant, I can figure out how much product, so water vapor is my product. I'm going to use hydrogen as my limiting reactant to figure out how much product is formed. So if I have 15 liters, as I do, of the hydrogen gas, and it's my limiting reactant, I'm then going to do a liter to liter ratio. I don't even need to convert it to moles. I can do a liter to liter ratio of between hydrogen gas and water. So 2 liters to 2 liters. So it's a 1-to-1 ratio, which ends up with 15 liters of water. So that was a very simple, quick understanding, as long as you can see that liter ratios are same as mole ratios, as long as temperature and pressure are constant. So you can treat it in the same way as the ratioing the moles. So the next part is to figure out what mass of oxygen reacted. So I'm going to take my limiting reactant, which is, I'm going to box this away, my 15 liters of hydrogen, and I'm going to liter ratio between hydrogen and oxygen. So for every 2 liters of hydrogen, there's 1 liter of oxygen. And then to get to mass, I then have to convert my liters to moles. So 1 liter or 1 mole has 22.4 liters. And then in 1 mole, there's 32 grams of oxygen. And my final answer is 10.7 grams of oxygen. Stoichiometry. So that's your stoich, and then your conversion using STP conditions right here. So a mole of any gas has 22.4 liters.